Falcon Heavy Test Flight Falcon Heavy Dummy Payload Falcon Heavy Flight 2. Falcon Heavy. The Falcon Heavy is a partially reusable heavy-lift launch vehicle designed and manufactured by SpaceX. It is derived from the Falcon 9 vehicle and consists of a strengthened Falcon 9 first stage as the center core with 2 additional first stages as strap-on boosters. The Falcon Heavy has the highest payload capacity of any currently operational launch vehicle, the second highest capacity of any rocket ever to reach orbit, trailing the Saturn V, and the third highest capacity of any orbital-class rocket ever launched, behind the Saturn V and Inertia. SpaceX conducted the Falcon Heavy's maiden launch on February 6, 2018, at 3:45 p.m. EST, 20:45 UTC. The rocket carried a Tesla Roadster belonging to SpaceX founder Elon Musk, as a dummy payload. The second Falcon Heavy launch occurred on April 11, 2019 and all 3 booster rockets successfully returned to Earth. The third Falcon Heavy launch successfully occurred on June 25, 2019. The Falcon Heavy was designed to carry humans into space beyond low Earth orbit, although as of February 2018, Musk does not plan to apply for a human rating certification to carry NASA astronauts. The Falcon Heavy and Falcon 9 will be replaced by the Starship and Super Heavy launch system. History. Concepts for a Falcon Heavy launch vehicle were initially discussed as early as 2004. The concept for 3 core booster stages of the company's as yet unflown Falcon 9 was referred to in 2005 as the Falcon 9 Heavy. SpaceX unveiled the plan for the Falcon Heavy to the public at a Washington, D.C. news conference in April 2011, with initial test flight expected in 2013. A number of factors delayed the planned maiden flight by 5 years to 2018, including 2 anomalies with Falcon 9 launch vehicles, which required all engineering resources to be dedicated to failure analysis, halting flight operations for many months. The integration and structural challenges of combining 3 Falcon 9 cores were much more difficult than expected. In July 2017, Elon Musk said, "It actually ended up being way harder to do Falcon Heavy than we thought, really way more difficult than we originally thought. We were pretty naive about that." The initial test flight for a Falcon Heavy lifted off on February 6, 2018, at 3:45 p.m. EST. Carrying its dummy payload, Musk's personal Tesla Roadster, beyond Mars orbit. Conception and funding. Musk mentioned Falcon Heavy in a September 2005 news update, referring to a customer request from 18 months prior. Various solutions using the planned Falcon 5, which was never flown, had been explored, but the only cost-effective, reliable iteration was one that used a 9-engine first stage, the Falcon 9. The Falcon Heavy was developed with private capital, with Musk stating that the cost was more than $500 million. No government financing was provided for its development. Design and development. The Falcon Heavy design is based on Falcon 9's fuselage and engines. By 2008, SpaceX had been aiming for the first launch of Falcon 9 in 2009, while Falcon 9 Heavy would be in a couple of years. Speaking at the 2008 Mars Society conference, Musk also indicated that he expected a hydrogen-fueled upper stage would follow 2 to 3 years later, which would have been around 2013. By April 2011, the capabilities and performance of the Falcon 9 vehicle were better understood, SpaceX having completed 2 successful demonstration missions to LEO, one of which included reignition of the second stage engine. At a press conference at the National Press Club in Washington, D.C. on April 5, 2011, Musk stated that Falcon Heavy would carry more payload to orbit or escape velocity than any vehicle in history, apart from the Saturn V moon rocket, and Soviet Inertia rocket. In the same year, with the expected increase in demand for both variants, SpaceX announced plans to expand manufacturing capacity as we build towards the capability of producing a Falcon 9 first stage or Falcon Heavy side booster every week and an upper stage every 2 weeks. In 2015, SpaceX announced a number of changes to the Falcon Heavy rocket, worked in parallel to the upgrade of the Falcon 9 V1.1 launch vehicle. In December 2016, SpaceX released a photo showing the Falcon Heavy interstage at the company headquarters in Hawthorne, California. Testing. By May 2013, a new, partly underground test stand was being built at the SpaceX Rocket Development and Test Facility in McGregor, Texas, specifically to test the triple cores and 27 rocket engines of the Falcon Heavy. By May 2017, SpaceX conducted the first static fire test of flight design Falcon Heavy center core at the McGregor facility. In July 2017, Musk discussed publicly the challenges of testing a complex launch vehicle like the three-core Falcon Heavy, indicating that a large extent of the new design is really impossible to test on the ground and could not be effectively tested independent of actual flight tests. By September 2017, all three first-stage cores had completed their static fire tests on the ground test stand. The first Falcon Heavy static fire test was conducted on January 24, 2018. Maiden flight. In April 2011, Musk was planning for a first launch of Falcon Heavy from Vandenberg Air Force Base on the West Coast in 2013. SpaceX refurbished Launch Complex 4 at Vandenberg AFB to accommodate Falcon 9 and Heavy. The first launch from the Cape Canaveral East Coast Launch Complex was planned for late 2013 or 2014. Due partly to the failure of SpaceX CRS-7 in June 2015, SpaceX rescheduled the maiden Falcon Heavy flight in September 2015 to occur no earlier than April 2016, but by February 2016 had postponed it again to late 2016. The flight was to be launched from the refurbished Kennedy Space Center Launch Complex 39A. In August 2016, the demonstration flight was moved to early 2017, then to summer 2017, to late 2017 and was launched in February 2018. A second flight occurred on April 11, 2019, launching Arabsat 6A. A third flight occurred on June 25, 2019, launching the STP-2, DoD Space Test Program, payload. The payload was composed of 25 small spacecraft. Operational GTO missions for Intelsat and Inmarsat, which were planned for late 2017, were moved to the Falcon 9 full-thrust rocket version as it had become powerful enough to lift those heavy payloads in its expendable configuration. At a July 2017 meeting of the International Space Station Research and Development meeting in Washington, D.C., Musk downplayed expectations for the success of the maiden flight. "There's a real good chance the vehicle won't make it to orbit. I hope it makes it far enough away from the pad that it does not cause pad damage. I would consider even that a win, to be honest." Musk went on to say the integration and structural challenges of combining three Falcon 9 cores were much more difficult than expected. The plan was for all three cores to land back on Earth after launch. In December 2017, Musk tweeted that the dummy payload on the maiden Falcon Heavy launch it would be his personal Tesla Roadster playing David Bowie's Life on Mars, and that it would be launched into an orbit around the Sun that will reach the orbit of Mars. He released pictures in the following days. The car had 3 cameras attached to provide epic views. On December 28, 2017, the Falcon Heavy was moved to the launch pad in preparation of a static fire test of all 27 engines, which was expected on January 19, 2018. However, due to the U.S. government shutdown that began on January 20, the testing and launch were further delayed. The static fire test was conducted on January 24, 2018. Musk confirmed via Twitter that the test was good and later announced the rocket would be launched on February 6. On February 6, 2018, after a delay of over 2 hours due to high winds, Falcon Heavy lifted off at 3:45 p.m. EST. Its side boosters landed safely on landing zones 1 and 2 a few minutes later. However, only one of the 3 engines on the central booster that were intended to restart ignited during its descent, causing it to hit the water next to the drone ship at a speed of over 480 km per hour, 300 miles per hour. Initially, Elon Musk tweeted that the Roadster had overshot its planned heliocentric orbit, and would reach the asteroid belt. In fact, observations by telescopes shows that the Roadster would only slightly exceed the orbit of Mars at aphelion. Design. The heavy configuration consists of a structurally strengthened Falcon 9 as the core component, with two additional Falcon 9 first stages acting as liquid fuel strap-on boosters, which is conceptually similar to ELV Delta IV Heavy launcher and proposals for the Atlas V Heavy and Russian Angara A5V. Falcon Heavy has more lift capability than any other operational rocket, with a payload of 64,000 kilograms, 141,000 pounds, to low Earth orbit and 16,800 kilograms, 37,000 pounds, to trans-Mars injection. The rocket was designed to meet or exceed all current requirements of human rating. The structural safety margins are 40% above flight loads, higher than the 25% margins of other rockets. Falcon Heavy was designed from the outset to carry humans into space, and it would restore the possibility of flying crewed missions to the Moon or Mars. The first stage is powered by 3 Falcon 9 derived cores, each equipped with 9 Merlin 1D engines. The Falcon Heavy has a total sea level thrust at liftoff of 22,819 kilonewtons, 5,130,000 lbf, from the 27 Merlin 1D engines, while thrust rises to 24,681 kilonewtons, 5,549,000 lbf, as the craft climbs out of the atmosphere. The upper stage is powered by a single Merlin 1D engine modified for vacuum operation, with a thrust of 934 kilonewtons, 210,000 lbf, an expansion ratio of 117:1 and a nominal burn time of 397 seconds. At launch, the center core throttles to full power for a few seconds for additional thrust, then throttles down. This allows a longer burn time. After the side boosters separate, the center core throttles back up to maximum thrust. For added reliability of restart, the engine has dual redundant Biorfark igniters, TTEB. The interstage, which connects the upper and lower stage for Falcon 9, is a carbon fiber aluminum core composite structure. Stage separation occurs via reusable separation collets and a pneumatic pusher system. The Falcon 9 tank walls and domes are made from aluminum lithium alloy. SpaceX uses an all-friction stir-welded tank. The second stage tank of Falcon 9 is simply a shorter version of the first stage tank and uses most of the same tooling, material, and manufacturing techniques. This approach reduces manufacturing costs during vehicle production. All 3 cores of the Falcon Heavy arrange the engines in a structural form SpaceX calls Octave, aimed at streamlining the manufacturing process, and each core includes 4 extensible landing legs. To control the descent of the boosters and center core through the atmosphere, SpaceX uses small grid fins which deploy from the vehicle after separation. Immediately after the side boosters separate, the center engine in each burns for a few seconds in order to control the booster's trajectory safely away from the rocket. The legs then deploy as the boosters turn back to Earth, landing each softly on the ground. The center core continues to fire until stage separation, after which its legs deploy and land back on Earth on a drone ship. The landing legs are made of carbon fiber with aluminum honeycomb structure. The 4 legs stow along the sides of each core during liftoff and later extend outward and down for landing. Rocket specifications. Falcon Heavy specifications and characteristics are as follows. The Falcon Heavy uses a 4.5 meter, 15 feet, interstage attached to the first stage core. It is a composite structure consisting of an aluminum honeycomb core surrounded by a carbon fiber face sheet plies. The overall length of the vehicle at launch is 70 meters, 230 feet, and the total fueled mass is 1,420,000 kilograms, 3,130,000 pounds. Without recovery of any stage, the Falcon Heavy can inject a 63,800 kilograms, 140,700 pounds, payload into a low Earth orbit, or 16,800 kilograms, 37,000 pounds, to Venus or Mars. The Falcon Heavy includes first stage recovery systems, to allow SpaceX to return the first stage boosters to the launch site as well as recover the first stage core following landing at an autonomous spaceport drone ship barge after completion of primary mission requirements. These systems include 4 deployable landing legs, which are locked against each first stage tank core during ascent. Excess propellant reserved for Falcon Heavy first stage recovery operations will be diverted for use on the primary mission objective, if required, ensuring sufficient performance margins for successful missions. The nominal payload capacity to a geostationary transfer orbit, GTO, is 8,000 kilograms, 18,000 pounds. With recovery of all 3 first stage cores, the price per launch is $90 million, versus 26,700 kilograms, 58,900 pounds, in fully expendable mode, $150 million price per launch. The Falcon Heavy can also inject a 16,000 kilograms, 35,000 pounds, payload into GTO if only the 2 boosters are recovered. Capabilities. The partially reusable Falcon Heavy falls into the heavy lift range of launch systems, capable of lifting 20 to 50 metric tons into low Earth orbit, LEO, under the classification system used by a NASA Human Spaceflight Review Panel. A fully expendable Falcon Heavy may also reach the super heavy lift category, above 50 metric tons to LEO. The initial concept, Falcon 9S9 2005, envisioned payloads of 24,750 kilograms, 54,560 pounds, to LEO, but by April 2011 this was projected to be up to 53,000 kilograms, 117,000 pounds, with GTO payloads up to 12,000 kilograms, 26,000 pounds. Later reports in 2011 projected higher payloads beyond LEO, including 19,000 kilograms, 42,000 pounds, to geostationary transfer orbit, 16,000 kilograms, 35,000 pounds, to translunar trajectory, and 14,000 kilograms, 31,000 pounds, on a trans-Martian orbit to Mars. By late 2013, SpaceX raised the projected GTO payload for Falcon Heavy to up to 21,200 kilograms, 46,700 pounds. In April 2017, the projected LEO payload for Falcon Heavy was raised from 54,400 kilograms, 119,900 pounds, to 63,800 kilograms, 140,700 pounds. The maximum payload is achieved when the rocket flies a fully expendable launch profile, not recovering any of the 3 first stage boosters. With just the core booster expended, and 2 side boosters recovered, Musk estimates the payload penalty to be around 10%, which would still yield over 57 metric tons of lift capability to LEO. Returning all 3 boosters to the launch site rather than landing them on drone ships would yield about 30 metric tons of payload to LEO. Reusability. From 2013 to 2016, SpaceX conducted parallel development of a reusable rocket architecture for Falcon 9, that applies to parts of Falcon Heavy as well. Early on, SpaceX had expressed hopes that all rocket stages would eventually be reusable. SpaceX has since demonstrated routine land and sea recovery of the Falcon 9 first stage, and has made attempts to recover the payload fairing. In the case of Falcon Heavy, the 2 outer cores separate from the rocket earlier in the flight, and are thus moving at a lower velocity than in a Falcon 9 launch profile. For the first flight of Falcon Heavy, SpaceX had considered attempting to recover the second stage, but did not execute this plan. SpaceX has indicated that the Falcon Heavy payload performance to geosynchronous transfer orbit, GTO, will be reduced due to the addition of the reusable technology, but the rocket would fly at a much lower price. When recovering all 3 booster cores, GTO payload is 8,000 kilograms, 18,000 pounds. If only the 2 outside cores are recovered while the center core is expended, GTO payload would be approximately 16,000 kilograms, 35,000 pounds. As a comparison, the next heaviest contemporary rocket, the fully expendable Delta IV Heavy, can deliver 14,210 kilograms, 31,330 pounds, to GTO. propellant crossfeed. Falcon Heavy was originally designed with a unique propellant crossfeed capability, whereby the center core engines would be supplied with fuel and oxidizer from the two side cores until their separation. Operating all engines at full thrust from launch, with fuel supplied mainly from the side boosters, would deplete the side boosters sooner, allowing their earlier separation. This would in turn leave most of the center core propellant available after booster separation, with a lighter load to accelerate. The propellant crossfeed system was originally proposed in a 1998 book on orbital mechanics by Tom Logsdon, and nicknamed asparagus staging. Musk stated in 2016 that crossfeed would not be implemented. Instead, the center booster throttles down shortly after liftoff to conserve fuel, and resumes full thrust after the side boosters have separated. Environmental impact. BBC Science Focus, in February 2018, published an article on Falcon Heavy's environmental impact. It stated concerns that frequent Falcon Heavy launches can contribute to pollution in the atmosphere. The Planetary Society was concerned that launching a non-sterile object, as was done on the Falcon Heavy test flight, to interplanetary space may risk biological contamination of a foreign world. Scientists at Purdue University thought it was the dirtiest man-made object ever sent into space, in terms of bacteria amount, noting the car was previously driven on Los Angeles freeways. Although the vehicle will be sterilized by solar radiation over time, some bacteria might survive on pieces of plastic which could contaminate Mars in the distant future. A study conducted by the Federal Aviation Administration found that the boost back and landing of Falcon Heavy boosters would not significantly affect the quality of the human environment. Launch prices. At an appearance in May 2004 before the United States Senate Committee on Commerce, Science, and Transportation, Musk testified, long-term plans call for development of a heavy lift product and even a super heavy, if there is customer demand. We expect that each size increase would result in a meaningful decrease in cost per pound to orbit. Ultimately, I believe $500 per pound or less is very achievable. This $1,100 per kilogram, $500 per pound, goal stated by Musk in 2011 is 35% of the cost of the lowest cost per pound LEO-capable launch system in a Circa 2000 study, the Zenit, a medium-lift launch vehicle that can carry 14,000 kilograms, 30,000 pounds, into LEO. As of March 2013, Falcon Heavy launch prices were below $2,200/kg, $1,000 per pound, to low Earth orbit when the launch vehicle is transporting its maximum delivered cargo weight. The published prices for Falcon Heavy launches have changed somewhat from year to year, with announced prices for the various versions of Falcon Heavy priced at $80 to $125 million in 2011, $83 to $128 million in 2012, $77 to $135 million in 2013, $85 million for up to 6,400 kilograms, 14,100 pounds, to GTO in 2014, $90 million for up to 8,000 kilograms, 18,000 pounds, to GTO in 2016, and $150 million for 63,800 kilograms, 140,700 pounds, to LEO or 26,700 kilograms, 58,900 pounds, to GTO, fully expendable, or $95 million for 90% of its maximum capacity in 2018. Launch contracts typically reflect launch prices at the time the contract is signed. In 2011, SpaceX stated that the cost of reaching low Earth orbit could be as low as $2,200/kg, $1,000 per pound, if an annual rate of 4 launches can be sustained, and as of 2011 plan to eventually launch as many as 10 Falcon Heavies and 10 Falcon 9s annually. A third launch site, intended exclusively for SpaceX private use, is planned at Boca Chica Village, Texas. SpaceX started construction on the third Falcon Heavy launch facility in 2014, with the first launches from the facility no earlier than late 2018. In late 2013, SpaceX had projected Falcon Heavy's inaugural flight to be in 2014, but it did not occur until February 2018 due to limited manufacturing capacity and the need to deliver on the Falcon 9 launch manifest. By late 2013, SpaceX prices for space launch were already the lowest in the industry. SpaceX's price for reused spacecraft could be reduced up to 30% short term, and potentially even further in the future. Launches and payloads. Due to improvements to the performance of Falcon 9, some of the heavier satellites flown to GTO, such as Intelsat 35E and Inmarsat 5F4, ended up being launched before the debut of Falcon Heavy. SpaceX anticipated the first commercial Falcon Heavy launch it would be 3 to 6 months after a successful maiden flight, but due to delays the first commercial payload, Arabsat 6A, was successfully launched on April 11, 2019, a year and 2 months after the first flight. Ovsn had also signed an agreement in 2018 to launch on top of Falcon Heavy in 2020, but they later cancelled the agreement. First commercial contracts. In May 2012, SpaceX announced that Intelsat had signed the first commercial contract for a Falcon Heavy flight. It was not confirmed at the time when the first Intelsat launch would occur, but the agreement will have SpaceX delivering satellites to Geosynchronous Transfer Orbit, GTO. In August 2016, it emerged that this Intelsat contract had been reassigned to a Falcon 9 full-thrust mission to deliver Intelsat 35E into orbit in the third quarter of 2017. Performance improvements of the Falcon 9 vehicle family since the 2012 announcement, advertising 8,300 kilograms to GTO for its expendable flight profile, enabled the launch of this 6,000 kilograms satellite without upgrading to a Falcon Heavy variant. In 2014, Inmarsat booked 3 launches with Falcon Heavy, but due to delays they switched a payload to Ariane 5 for 2017. Similarly to the Intelsat 35E case, another satellite from this contract, Inmarsat 5F4, was switched to a Falcon 9 full thrust thanks to the increased liftoff capacity. The remaining contract covers the launch of Inmarsat 6F1 in 2020 on a Falcon 9. First DoD contract, USAF. In December 2012, SpaceX announced its first Falcon Heavy launch contract with the United States Department of Defense, DoD. The United States Air Force Space and Missile Systems Center awarded SpaceX 2 Evolved Expendable Launch Vehicle, EELV class missions, including the Space Test Program 2, STP-2, mission for Falcon Heavy, originally scheduled to be launched in March 2017, to be placed at a near-circular orbit at an altitude of till to 700 kilometers, with an inclination of 70 degrees. In April 2015, SpaceX sent the U.S. Air Force an updated letter of intent outlining a certification process for its Falcon Heavy rocket to launch national security satellites. The process includes 3 successful flights of the Falcon Heavy, including 2 consecutive successful flights, and the letter stated that Falcon Heavy can be ready to fly national security payloads by 2017. But in July 2017, SpaceX announced that the first test flight would take place in December 2017, pushing the launch of the second launch, Space Test Program 2, to June 2018. In May 2018, on the occasion of the first launch of the Falcon 9 Block 5 variant, a further delay to October 2018 was announced, and the launch was eventually pushed back to June 25, 2019. The STP-2 mission used 3 Block 5 cores. STP-2 payload. The payload for the STP-2 mission included 25 small spacecraft from the U.S. military, NASA, and research institutions. The Green Propellant Infusion Mission, GPIM, was a payload. It is a project partly developed by the U.S. Air Force to demonstrate a less toxic propellant. Another secondary payload is the miniaturized deep space atomic clock that is expected to facilitate autonomous navigation. The Air Force Research Laboratory's Demonstration and Science Experiments, DSX, has a massive 500 kilograms and will measure the effects of very low frequency radio waves on space radiation. The British orbital testbed payload is hosting several commercial and military experiments. Other small satellites included PROX-1, built by Georgia Tech students to test out a 3D printed thruster and a miniaturized gyroscope, LightSail by the Planetary Society, Oculus ASR nanosatellite from Michigan Tech, and CubeSats from the U.S. Air Force Academy, the Naval Postgraduate School, the Naval Research Laboratory, the University of Texas at Austin, Cal Poly, and a CubeSat assembled by students at Merritt Island High School in Florida. The Block 5 second stage allowed multiple range missions to place its mini payloads in multiple orbits. The launch was planned to include a 5,000 kg ballast mass, but the ballast mass was later omitted from the 3,700 kg total mass for the payload stack. Solar System Transport Missions. In 2011, NASA Ames Research Center proposed a Mars mission called Red Dragon that would use a Falcon Heavy as the launch vehicle and Trans-Martian injection vehicle, and a variant of the Dragon capsule to enter the Martian atmosphere. The proposed science objectives were to detect biosignatures and to drill 1 meter, 3.3 feet, or so underground, in an effort to sample reservoirs of water ice known to exist under the surface. The mission cost as of 2011 was projected to be less than $425 million, not including the launch cost. SpaceX 2015 estimation was 2,000 to 4,000 kilograms, 4,400 to 8,800 pounds, to the surface of Mars, with a soft retro-propulsive landing following a limited atmospheric deceleration using a parachute and heat shield. Beyond the Red Dragon concept, SpaceX was seeing potential for Falcon Heavy and Dragon 2 to carry science payloads across much of the solar system, particularly to Jupiter's moon Europa. SpaceX announced in 2017 that propulsive landing for Dragon 2 would not be developed further, and that the capsule would not receive landing legs. Consequently, the Red Dragon missions to Mars were cancelled in favor of the BFR, a larger vehicle using a different landing technology.